Hello everyone, welcome to Circles Part 2. In this session, we will learn few more theorems. So let us start with the theorem 1. In this session, equal chords of a circle are equidistant from the center. This is a theorem statement. To prove this, let us take a circle and draw chords and name it as AB, CD. Take a center O and the line joining O to this point X and Y. So what is given in this theorem? It is given that AB is equal to CD and OX and OY are perpendiculars. This and this are perpendicular. That is OX is perpendicular to AB and OY is perpendicular to CD. This is what is given. And what is our RTP in this theorem? We have to prove that OX is equal to OY. We have to prove. And to proceed for the proof, let us take the perpendiculars. What is given? OX is perpendicular to AB is given and OY is perpendicular to CD is given. And we know that the perpendiculars from the center to the chord bisects the chord. So based on this, we have AX is equal to BX, which is equal to AB by 2. So let us take this as equation 1. And similarly, we have CY is equal to DY, which is equal to CD by 2. Let us take this as equation 2. Now what is given? And we have AB equals to CD. And if I divide by 2, what will I get? I will get, comparing equation 1 and 2, I get AX is equal to C1. We got AX equals to C1. Now we compare these two triangles, which we get by joining AO and CO. We get two triangles, that is triangle AOX and triangle COY. When we compare, in this we know that one angle is 90 degrees and OA is equal to OC, OA is equal to OC and AX is equal to C1. So based on RHS congruency rule, we can say that these two triangles are congruent. Now, since these two triangles are congruent, based on the CPCT, we get OX is equal to OY. Hence, we have proved that equal chords of circle are equidistant from the center. So, let us take the next theorem. Next theorem states that chords equidistant from the center of a circle are equal in length. Chords equidistant from the center of a circle are equal in length. If we notice, this is exactly opposite to the previous theorem. So for this, let us take a circle and do a little construction to proceed with the proof. So let us draw the chords and name it as AB and CD. Take a center O and join this OX and name it as OY. And now what is given in this theorem? It is given that a circle and AB and CD. AB and CD are chords. And we know that OX is perpendicular to AB and OY is perpendicular to CD. And that means OX is equal to OY. This is given. And what we have to prove, that is our RTP in this theorem is, we have to prove that chords are equal, that is AB is equal to CD. So to proceed for the proof, let us do a construction, that is join AO and DO. We get two triangles. So when we compare these two triangles, AOX and triangle DOY, in these two triangles, the angles are equal, that is perpendicular, it's given, and OA is equal to OD. OA is equal to OD and OX is equal to OY. This is also given. Therefore, according to RHS congruency rule, these two triangles become congruent and we have AX is equal to DY. So let us take this as statement 1. And we know that OX is perpendicular to AB. OX is perpendicular to AB and similarly we have OY also perpendicular to CD. And since we know that the perpendiculars from the center to the chord bisects the chord, we know that X bisects here AB and Y bisects CD. Therefore, we have AB equals to, therefore we get AB is equal to 2 times of AX and we get CD is equal to 2 times of DY. Now as AX is equal to DY, from here, and if I write 2 times of AX is equal to 2 times of AY. Yes, what is 2 times of AX here? 2 times of AX is nothing but our AB and 2 times of D1 is equal to CD. Therefore, we have proved that the chords are equal in length. So this is our second theorem. Now let us take the next theorem. The theorem states that the angle subtended by an arc at the center is double the angle subtended by it at any point on the remaining part of the circle. I repeat the statement. The angle subtended by an arc at the center is double the angle subtended by it at any point on the remaining part of the circle. So this is our theorem statement. For this, let us do some construction in the circle which helps us to proceed with the proof. So according to the theorem, we need to take an angle. First we will take point A, P and Q and join. We get the line segments and take the center and make it as O and join P to O and Q to O. So this is our construction needed to proceed with the proof. So what is given? So first let us know that arc PQ of the circle. So arc PQ of the circle is subtending angle POQ at the center. So this is the angle formed with this arc. And angle PAQ at a point A with the remaining part of the circle. So PQ is making two angles. One is this angle and one is this arc, and the other angle is this. So now we have to prove that angle POQ is two times the angle PAQ. So this is what we have to prove. So what is the construction we have done? Little construction we will do. Further still, we will extend this point till P. So always we do the construction needed which is beyond the theorem statement with the dotted lines. So let us take two general cases. This is case 1 we will consider, and we will take another case with the same circle, and as I'll take another case for the same circle and the point, and I'll join this and the center. So this is another case. So we will study now case 1 and case 2. So in case 1, what have we done? So case 2 we will proceed later once we complete case 1. So in case 1, that is in the first condition, in triangle APO. So what do we get? A triangle APO and in triangle AQO. APO and AQO. If you compare, we have OP equals to OA and OQ is equal to area, both from the radius. And we know that angle OEA is equal to angle OAP. That is, the angles opposite to equal sides are equal. Similarly, here we get angle OQA is equal to angle OAQ. And also by the exterior angle property, we get angle BOP is equal to angle OPA plus angle OAP. Similarly, here also based on the exterior angle property, BOQ is equal to angle OQA plus angle OAQ. And Since after substituting this in both the statements, we get angle BOP is equal to 2 times of angle OAP. Here also we get angle POQ is equal to 2 times of angle OAQ. Now when we compare these two, and add, we get, by adding we get angle BOP plus angle BOQ. BOP plus BOQ, we will be getting the entire angle BOQ. And the right hand side when we add, that is 2 times of angle OAP plus 2 times of angle OAQ gives us 2 times of angle PAQ. So hence we have proved that the angle subtended by the arc at the center is double the angle subtended by it at any point on the remaining part of the circle. And if we take case 2 as we have done the diagram, we will change a little to understand the case 2. Case 2 in the sense there may be another option, that is the angle formed as in the case 2. We will see what is the other possibility in this. Yeah, in case 2 we will just change the figure. I take a point A, P, Q and the center. I'll get a figure like this, a quadrilateral you can see, and I just extend this as I have taken in the previous proof. Yeah, here again we will get 2 triangles. One is, let's make the center as O. We will compare 2 triangles, triangle APO and triangle AQO again. So if we compare, we have OP equals to OA and OQ is equal to OA as they form the radius. And we know that angle OBA is equal to angle OAB. That is angle opposite to equal sides are equals. So similarly, here we get OQA is equal to OAQ. And also by the exterior angle property, as we have done in the previous case, we get angle BOP is equal to angle OBA plus angle OAB. Here we get angle BOQ is equal to angle OQA plus angle OAQ. OAQ and OBA. Now, when we substitute this in this equation and this in this equation, we get BOP is equal to 2 times of angle OAP. Here we get angle BOQ equals to 2 times of angle OAQ. Now, if we add these two equations, this one and this one, what do we get? We get BOP plus BOQ. BOP plus BOQ will be equal to the total angle. What is that angle? Angle BOP plus angle BOQ is equal to 2 times of that angle OAP plus OAQ, which is equal to 2 times of angle PAQ, which is the exterior angle here. So this is nothing but 360 degrees minus angle POQ we get, which is equal to 2 times of angle PAQ. Hence, we have that the exterior angle here, which we got it as a reflex angle, angle POQ is equal to 2 times of angle PAQ. That is, the angle subtended by an arc at the center is double the angle subtended by it at any point on the remaining part of the circle. So as we have two possibilities, we have proved the two cases. Thank you.